Hello, everyone, and welcome to part 2 of section 1 for the Abstract Modern Algebra lecture series. So in part 1, we talked about symmetries and dihedral groups. So now we will talk about groups. So let's look at a definition and see what a group is. So a group is a set of one functions on finite sets that could be grouped together to form a set that is closed under composition. And another thing to note about groups can have binary operations associated with them. And we kind of went over this a little bit when we were looking at the Cayley table in part 1. Not about the binary operations, but the fact that the group is closed under composition. But binary operations are a new thing that we're going to look at for this part. And we are actually going to look at what a binary operation is. So a binary operation is a function on a set. Let's call it G, at least for this definition, that assigns each ordered pair of elements of G an element of G. And of course, this is also called closure. And such operations include addition, subtraction, and multiplication of integers. And the notation for a group like this is kind of like how you would write an ordered pair, because I mean technically that's kind of what it is, but you would just have two blanks here, and this would be your set, and then this would be your operation. Would fill in those blanks. So let's look at an example of this. So we have integers with addition operation. So the set of integers under addition operation. And then this one would be the set of rationals under multiplication operation. And sometimes you'll see for multiplication, you may see the solid dot used, but sometimes people also use the star to represent the multiplication operation. You'll probably see both as we go throughout this course. I may vice versa use them. All right, so those are some examples of groups under a binary operation. So, or sets under a binary operation, because so if we have a certain number n where the set is 0, 1, 2, so on and so forth, up to n minus 1, we can denote it with a subscript n for some groups. So an example could be z of n, which can refer to an addition operation and a multiplication operation might be written as zn with the multiplication operation of n. All right, so let's look at what defines a set as a group. A set is a group if it satisfies the following three conditions. And we kind of briefly went over these in part 1, 2, but now we'll look at them a little more in depth. The first one is associativity. So for a set G and elements A, B, C, A times B times C is equal to A times BC. for all A, B, C in G. And then we have an identity. So for a set G, there is an element E such that AE equals A equals A for all A in G. And then the third one is inverses. So for a set G, there is an element B in G such that AB equals B, A equals E for all A in G. So these are the three key properties on top of closure that you want to look for to see if a set is a group. Additionally, groups can also be abelian or commutative. So if you recall from part 1, if AB equals BA for all A and B in a group, it is abelian. And if this property is not true, it is non-abelian. All right, so that is the important thing to look at for groups. So now we will change colors here and look at another topic, and that topic is going to be, which color am I going to choose? I guess we'll go with sky blue. We will look at elementary properties of groups. All right, so we will look at and prove the properties / conditions of groups, associativity, identities, inverses, closure, and then we will look at a few examples of binary operations and determine if they are groups. So let's look at some theorems first before we look at the examples. So here's one theorem. In a group G, there is only one identity element. So let's look at the proof for this. So let's let G be a group and A be an element of G. So let's suppose both E and E prime are identities of G. So then we have A of E equals A for all A in G, and E prime A equals A for all A in G. So there we go. So hence E prime of E equals E, and E prime equals E times E prime. So therefore E equals E prime, and G has only one identity element as desired. Let's look at another theorem. So in a group G, the right and left cancellation holds, cancellation laws hold. So that is BA equals CA implies B equals C, and AB equals AC implies B equals C. So let's look at a proof of this theorem. So we will let G be a group and A, B, and C be elements of G. So let's suppose BA equals CA, and then we will let A prime be the inverse of A, so then we have BA times A prime equals CA times A prime by associativity, and then we have sorry, got that out of order. But then let's change the transition word. So let's say hence BA A prime equals CA A prime by associativity. Yes, this is using associativity. And then this implies that B equals CE, which implies that B equals C. And now let's suppose that AB equals AC. So then we have AB A negative 1 equals AC A times A inverse. I guess technically that's the correct way to describe it, is A inverse. Then we can use associativity again to pair A and its inverse together, which will give us it's supposed to be BE equals CE, which implies that B equals C as desired. Yep. So for groups, you have a left and right cancellation. So if you have elements being composed with the same element, then they should both imply each other. All right, now let's go through another theorem. So for each element A in a group G, there is a unique inverse or unique, unique element in G such that AB equals B, A equals E. So let's look at the proof of this. So again, we will let G be a group and A, B, C be elements of G. So let's suppose B and C are inverses of A. So then AB equals E and AC equals E. So hence we have AB equals AC implies that B equals C as desired. So this proof kind of builds off of what we went over on the previous theorem about left and right cancellation. So since B and C are both defined as inverses here, and we can do left and right cancellation. Of course, I could have written it out, but we can imply it since we've already written the theorem out, and that will lead us to B equals C, which means that there is a unique element or a unique inverse for each element. So, all right, let's see here. I have one more theorem, and then we will look at the examples for this. And then we will be finished up with section 1. So let's take a look at this last theorem. So we have for group elements A and B, AB inverse is equal to the inverse of B goes with the inverse of A. So let's look at the proof of this. Oh yeah, by the way, this is known as the Sachs-Shoes property too. Just thought that was a neat little name for this. Just try to draw some shoes here. Then we'll try to doodle out some socks too. Well, best socks that I could doodle out. All right, so the proof, we are going to let A and B be group elements, and A inverse and B inverse be inverses of A and B. So then we have AB, and then we'll have their inverses. Because usually when you have the element present, you can often imply that their inverses are present as well. Since these are group elements, we will do some associativity here. And this will give us the identity element. And then we also have that these equal the identity element. So since AB and its inverse equals the identity element, then we can imply that the inverse of A and B is equal to A inverse B inverse as desired. All right, so that is it for some theorems and some proofs. So now let's look at an example. So here's our example. So we need to determine if the following three sets are groups. So first thing we have is integers under ordinary addition, which of course can be written out as this ordered pair, this set with the binary operation. We have 5 by 5 real matrices with multiplication and a determinant of 1, and this can be often written as SL5 with the real number set, and this is notation for a special linear or SL set of matrices. And then the third one that they want us to look at is complex numbers under multiplication, or shorthand notation, complex numbers with multiplication binary operation. So let's solve these. So let's start with part A. We have integers with the binary operation of addition. So we first check for closure. So let's let A and B be elements of Z. So then A plus B is also an integer. So the binary operation is closed. So we have closure. The next property we're going to look at is well, sorry. First we check for closure, and now we'll go and look at our three key properties. So we are looking for associativity. So let's let A, B, and C be integers. So then we have A plus B plus C is an integer, and A plus B plus C is an integer. So we have A plus B plus C equals A plus B plus C. So we have associativity. This property is satisfied. So next, let's see if we have an identity. So let's let A be an integer. So then we have 0 plus A equals A. So 0 is an identity. So we have an identity. And then let's look at inverses. So let's let A be an integer. So then we have A plus negative A be equal to 0, where negative A is an integer. So we have inverses for our elements. So what we can conclude is that Z with the binary operation of addition, or with the integers with binary operation of addition, is a group. All right, now let's look at our second set. So let's check for, let's look at what we're looking at. We're going to have 5 by 5 real matrices with multiplication and a determinant of 1. This is a special linear set of matrices. So let's first check for closure. Under our multiplication binary operation, so we need to let A and B be elements of our special linear group. So then we have the determinant of A and B equals to the determinant of A multiplied by the determinant of B, which should be equal to 1. And 1 equals 1, so we are good. We have closure. Now let's look at our key properties. So associativity. So let's let A, B, and C be an element of our special linear group. So we have A times BC equals AB times C. So associativity is satisfied. Let's check for identities, or for an identity. So let's let A, let's keep it capital since we're doing matrices, A be an element of our special linear group. So then we have A equals 1 times A. So we have 1 as an identity. All right, and then the last property to check for, we need to find if we have inverses. So we need to let A be an element of our special linear group. So then A inverse is an element of our special linear group. And the determinant of the inverse of A equals 1 over the determinant of A. This is a property of inverse of matrices, which for the special linear group is going to be 1. So we have inverses for every element of our group. So therefore, our special linear group, 5 by 5 real matrices, with the determinant of 1, is a group. All right, and then our last one. Let's look at our complex numbers with multiplication. So let's check for closure before we do our key properties. So closure is, we're going to let A plus BI be an element of the complex number set where A and B are real numbers. So then A plus BI times A plus BI will FOIL everything out. A squared plus 2ABI plus B squared I squared equals A squared plus 2A BI minus B squared. And this is still technically in the form A plus BI, which we need to be an element of the complex number set. So A squared plus 2ABI minus B squared is an element of the complex number set. And we have closure under our binary operation. Okay, now our key properties. So let's look at associativity. So let's let A plus BI and C plus DI and G plus HI be elements of complex numbers, or be complex numbers. So then we have A plus BI times C plus DI G plus HI is equal to A plus BI C plus DI times G plus HI. So we have associativity. Then identity. So let's let A plus BI be a complex number. Where A and B are real numbers. And I should probably include that up here too. where A, B, C, D, G, H are real numbers. So then we have A plus BI equals 1 times A plus BI, and 1 is an element of the complex number set, so 1 is an identity. Then we have, last thing we need to look for is inverses. So let's let A plus BI be a complex number. Where A and B are real numbers. So we have if A equals 0 and B equals 0, then there are no inverses because 0 does not have an inverse. So every element does not have an inverse. So the inverse property fails. And it was looking like this was about to be a group because we had closure, associativity, and an identity. But since every element does not have inverses, the complex numbers under multiplication is not a group. And that is it for this example. Alrighty. Hey guys, thank you so much for watching. And that is it for section 1 of the Abstract Modern Algebra lecture series. So I hope that you guys enjoyed these lectures, and I will see you in the examples video.